Okay, we were finding the mean square value at the quantization noise, and that comes out to be this, and you can further solve it. It becomes L by 2mp, that is pq of q, and integration of q squared will become q cube divided by 3, limits from minus mp to plus mp, and that will become L by 2mp into, sorry, this is mp by L to minus mp by L. You can take this 3 outside, divided by 3 mp by L cube minus mp by L cube. So this will become plus, and you get L by 6 mp into 2 times mp cube divided by L. Okay, and this L and this L will get cancelled, this 2 and 3, and this cancel the square. You'll get 1 by, sorry, this will become L cube, because it is mp by L cube minus mp by L cube. So you get 1 by 3 into mp by L square. Okay. This is your mean square value of the quantization noise, and accordingly you can find the variance. The variance, which is sigma q square, will be mean square value minus square of the mean. And if you see the mean of this PDF, it is 0. Okay, because it is a uniform PDF and the center of the PDF is at q is equal to 0, so the mean is 0. So the variance and the mean square value in this case is that is 1 by 3 into mp by L square. Okay, accordingly, if you will have a sinusoidal signal, you can find the signal power, which is basically a square by 2, and then this is the noise power, accordingly, which I say suppose n naught, and then you can define p naught by n naught, which we call as signal to quantization noise ratio. Okay. So again, see, we will have one more example. Like we have a problem that the output voltage of a sinusoidal generator is a naught, a cos omega naught t. So you have a sine wave generator, sinusoidal generator. The output of this is a cos omega t, and the output is sampled. So you have a switch, and this is measured using maybe V. V is a voltmeter. So you have a sinusoidal generator whose output is a cos omega t, and the output is, this is the output which is sampled. Output is sampled randomly. Okay, this is sampled. It is not a uniform sampling, and the sampled output, we call it as a random variable. The sampled output is a random variable x, which can take any value in the range minus a to plus a. and you have to find the mean value and the mean square value of this random variable x. Okay, this is the problem. So you have a sinusoidal generator. Which generates a sinusoidal wave. I can say it is like this, a periodic wave, which is a cos of omega t, and then this is sampled randomly. Okay, the sampling is not uniform. So suppose you take a sample here at 0, then you take at this point, then you take this point, or this point, and so on. Okay, sampling is not uniform. Sampling is random, like this. It means the switch that you have basically taken here, it opens and closes, okay, not periodically, but randomly. So that is how you get the samples of this continuous waveform. So you have a cos omega t and you are taking its samples randomly. The sampled output, these samples we are calling them as a random variable x, and definitely it can take any value between a and minus a. Minus a is the minimum amplitude and a is the maximum amplitude or maximum value of the random variable which it can take. So you have to find the mean and the variance of this, or mean and the mean square value of this random variable. Okay. So in this a cos omega t, if I take omega t as theta, which is basically the phase, okay, so you have a phasor, with a constant amplitude a, and it is rotating at a constant angular frequency which is omega. Okay, definitely this angle which is theta, which is going to be omega times t, and if you take the projection of this on this axis, that is how you get the cos component. Okay, now since I am taking this t, variable t, as random, it is not uniform, the samples are taken randomly, so this theta, it can take any value between 0 and 2 pi. Okay, so the range of theta will be between 0 and 2 pi, and between 0 and 2 pi it can take any continuous value. Okay, so like suppose if I take one sample at this time, then this is the value of theta. Another sample if I take at this point, then this is theta. Next sample I take at this point, at this time, then this is theta, and so on. Okay, so theta can take any value between 0 and 2 pi, and since the sampling is not uniform, it is randomly sampled, so this theta can take any random value between 0 and 2 pi. So I can say that the probability density function of theta, which I say p theta of theta, will be uniform between 0 and 2 pi, 1 by 2 pi, because the area has to be 1 of the PDF. Okay, so we have a cos omega t, which is a sinusoidal signal, and we are sampling it randomly. Okay, the sample so generated, we call it as a random variable x. But if you see these samples, they are basically a function of theta, and theta will have a uniform PDF between 0 and 2 pi, because t can take any random value, theta can also take any random value. Okay, so the probability of taking any value between 0 to pi, 0 to 2 pi will be same. So that is why you have a uniform PDF. Now x, the random variable x, which is a cos omega t, that can be taken as a cos of theta. So this random variable is basically a function of another random variable. Okay. So you have seen that if your x is a function of, when you have a function of a random variable, suppose we have a random variable x and we have another random variable y which is a function of x, then the mean of this random variable y is given by integral of g of x into p f x dx, and similarly the mean square value. Okay. So we have represented this random variable x as a function of another random variable theta. So this, the mean value of this random variable x bar will be integral of 0 to 2 pi x into p theta of theta into d theta, and that will become 1 by 2 pi integral from 0 to 2 pi a cos theta d theta. Okay, because x is your a cos theta and p theta is 1 by 2 pi that we have taken outside the integration, and this integration becomes 0. Okay, because integration of this function over one time period is 0. Likewise, you can find the mean square value, which is integral from 0 to 2 pi x square into p theta of theta into d theta, and in this case, since x is a cos theta, so you'll get a square divided by 2 pi. This 2 pi is from this 1 by 2 pi into integral of cos square theta d theta. Okay, so this cos square theta, you can write it as 2 cos theta minus 1, and then you can integrate it. It comes out to be a square by 2. So the mean value is 0 and the mean square value is a square by 2. And if you compare with the standard what we have studied in the signal and system theory, so if you have a cos omega ct and if you find the power of this signal, that power comes to be a square by 2. Okay, it is the same thing, but we have done it is in the form of random variables. Okay, so you have taken a cos omega t, which is a sinusoidal generator, a sinusoidal output. It is sampled randomly to generate a random variable x. X is equal to a cos omega t, where t can take any random value. And this omega t is represented as theta, which can take a value between 0 and 2 pi, and it will have a uniform PDF. Then definitely x will be a function of theta. So theta is a random variable, x is a function of another random variable, and that is how you find its mean and the variance of this random variable. Okay.